Hey there, I'm Spencer with Engineering Commons, and today we'll be taking a look at a modern interpretation of the Antikythera mechanism. Now there's been quite a bit of research done of the original device, and I've put some links in the description if you want to dig deeper, so we'll just cover the basics here. The name comes from the place it was discovered, a small island in Greece called Antikythera. It's Antikythera. And off the coast of Antikythera is the Antikythera shipwreck, and found inside of that was the Antikythera mechanism. It was recovered in 1901, and at the time looked like little more than a corroded lump of bronze. Since then it has fallen into more than 6 pieces. 2 millennia underwater has left it in pretty poor condition. But they did notice a gear early on, and that got historians very interested, as it was clearly from centuries before that sort of technology was believed to have been developed. There were theories that maybe it was a navigational instrument, but really nobody quite knew for sure. It wasn't until radiography was available in the 1970s that major strides were made into what exactly it was. These are the 3 largest of the 82 surviving pieces. Let's take a look at the most famous one in the center, Fragment A. You can plainly see a large drive wheel and a few smaller gears beneath it. But if we take a CT scan, an incredible amount of detail is revealed hidden underneath the corroded surface. Most importantly, individual gear teeth can be resolved, and after extrapolating the missing sections, the tooth count of each gear can be determined, which is crucial to revealing their function. Here's an example. This is a series of gears in Fragment A that form a gear train. If we count the teeth on each gear, that lets us determine the overall gear ratio, 254 to 19. For every 19 rotations of the yellow gear, the white gear turns 254 times. Measurement devices like clocks or sextants tend to have more straightforward divisions like 10 to 1 or 60 to 1, so 254 to 19 is very unusual. Now let's take a suspiciously unrelated tangent to talk about our solar system. Here we have the Sun, and here's the Earth, and of course it goes around in an orbit in a specific direction. Let's set that off to the left, and on the right we'll do the exact same thing with the Moon going around the Earth. Let's fast forward exactly 1 solar year, until the Earth is right back where it started. At the end of that year, you can see the number of lunar months is not a nice integer. This is a challenge with lunisolar calendars that use both the moon and the sun, and requires complications with partial months or days not in any month to make everything line up at the end of the year. This is one of the reasons our Gregorian calendar eliminates lunar months entirely. But if we're patient and wait a bit longer, say another 18 years or so, we'll see something very interesting. It turns out that even though an even number of lunar months doesn't fit into a single solar year, there is still an integer relationship between the two that is remarkably accurate. 19 solar years is almost exactly 254 lunar months. This was referred to by the ancient Greeks as the Metonic cycle, and the basis for the Metonic calendar. An ancient Greek device so intentionally incorporating this fraction is almost certainly meant to relate the movement of the moon and the sun. Now we are only looking at how this particular fraction indicated the Metonic cycle, but this process was repeated all over the device. Starting from the 1-year main drive gear, the gear ratios of various trains were calculated, and from those the significance of the output could be determined. Many of these are displayed with pointers and dials on the back of the machine for the user to read. Now I mentioned at the beginning of this video that this would be a modern interpretation, and I'd like to explain what I meant by that. The Antikythera mechanism is an incredibly ingenious device for its time, and there are certainly some people who have or are currently pursuing accurate reproductions of it. Most notable are the models made by Michael Wright and the ongoing video series by Chris of ClickSpring. But I wanted to do something a little different to adjust the design for a hobby machinist like myself. It goes without saying that 2,000 years has brought tremendous advances in materials, tooling, and astronomy, and there are a few things that I felt were worth adjusting. I've separated these into two categories: ease of use changes that make the device easier to make, maintain, and demonstrate, and what I'm calling just for fun changes, where I took some creative license for the purpose of aesthetics and my own learning. To start, the materials used in the original are believed to have been a low tin bronze, likely hammered into sheet stock from which the plates and gears were cut. I elected to use brass instead for primarily cost reasons, starting from a combination of plate, rod, and tube stock. Additionally, as the original is known to have suffered from friction buildup, I've changed most of the rotating and bearing interfaces to be stainless on brass to reduce the friction coefficient and keep things running smoothly. Now this next one might be a bit contentious among Antikythera purists, as the triangular teeth of the original are very distinctive, but due to the risk of overwhelming friction, I decided to play it safe and use a modern involute tooth profile for all of the gears. Specifically, I used module 0.6 as a standard size, and module 0.4 and 0.8 in a couple select instances. At this point, I've mentioned friction a couple times, and it's worth pointing out what exactly is happening here. If we look at a conventional drivetrain, the power input is located on the fastest turning gear, seen here on the right. As we move away from there down the train, the frictional effect increases with each gear, but the torque also increases to help overcome it. However, the Antikythera mechanism has the hand crank on a slow gear. This is called a back-driven gear train. The friction increases going away from the driven gear just like before, but the torque instead decreases and eventually isn't enough to overcome the friction. This leaves the Antikythera mechanism susceptible to binding and requiring significant forces at the crank that can distort gears and strip gear teeth. The CT scans show evidence of bracing to the input gear that indicate the makers were aware of the issue and trying to address it. Thankfully, the material and gear profile changes were sufficient to address this issue on my build, but if you were to, as an example, 3D print the gears, you would definitely want to connect the crank to the rapid lunar indicator side of the assembly, or the teeth of gear D1 will quickly shear off. The next difference is a very common one. As I plan on sharing this model for demonstration purposes, I decided to forego the wooden enclosure of the original in favor of a more open design similar to a skeleton clock. There are just too many interesting motions inside the machine to keep them all hidden away. Another common change I also made was to incorporate modern fasteners for assembly. The original device predates screws like this by many centuries, instead making heavy use of riveting, soldering, and other irreversible assembly processes. Using screws allows for easy disassembly and reassembly for repair and maintenance work, not to mention reducing how much needs to be remade when mistakes inevitably occur during construction. The last ease of use change has to do with the pair of spiral dials on the back plate that indicate the metonic and Saros cycles. Each of these spirals has a rotating hub at the center, holding a sliding pointer with a pin at the end. As the hub rotates, the pin follows along the spiral, pulling the pointer out as it goes. Eventually, the pin gets to the end of the slot, and the operator must manually reposition the pin at the beginning of the spiral. However, with so many parts moving and dials on both sides, it's easy to not notice the pointer approaching the end of the spiral, and the leverage from the gears will quickly break the pin or pointer. Eliminating this singular manual operation seemed worthwhile, such that the device could be cranked indefinitely without fear of damage. The difficulty is that discontinuous movement like this is not trivial to mechanize, especially given that it needs to work running forward as well as backwards. The solution I arrived at was to add a rotating wire corkscrew above each pointer. It is a single-turn helix and uses a pair of bevel gears to rotate it slowly off of the pointer rotation. The 5-turn metonic spiral gets a 1:5 gear ratio, and the 4-turn Saros spiral gets a 1:4 gear ratio. The dial is read at the intersection of the pointer and the corkscrew, a point which moves slowly outward at the correct rate to follow the spiral, just like the pin of the original. Unlike the original, however, at the end of the spiral the corkscrew has completed a full turn and is back to its original state. That intersection is now back at the start of the spiral, and cranking the device can be continued uninterrupted and without risk of damage. Now that we've covered the ease of use changes, let's move on to the just for fun changes. The first one has to do with a portion of the mechanism called the Planetarium. The Planetarium is actually largely missing from the recovered fragments, but there are clear indications of its existence from both the inscriptions on the device, as well as broken off attachment points on the main drive wheel. Its purpose was to model the motion of the various celestial objects known at the time. The makers of the Antikythera mechanism would have had astronomical observations from Babylon to inform their understanding of these celestial motions, and from modern imaging of the main drive wheel we can get some dimensional information. Research on the device in the last 25 years has had a heavy focus on matching these two things together. With these locations and quantity of pivots and pillars, what gears and linkages could have been used to produce the desired motion? Now I am far from a historian, and do not have access to the full scan data of the device, so I consider this an opportunity to follow in the steps of the maker, but using modern orbital data in place of the Babylonian observations to derive the gearing and geometry from scratch. To get started, we'll take a look at the night sky, where we can see a whole host of bright objects, primarily stars. Some are planets, but right now we don't know which ones. Let's focus in on an arbitrary point in the sky for a closer look. Nothing is readily apparent now, but when we compare it to the next day, things get interesting. A few objects have shifted, and if we come back night after night, they all seem to be moving along a common line, generally in one direction, but occasionally reversing back during short retrograde periods. If we record the position along that line of Mercury, for example, we get a curve that looks like this, a generally increasing mean motion with a periodic motion layered on top of it. The planet appears to be going in reverse when the periodic motion temporarily overwhelms the mean motion. When we add on the other planets, Venus, Mars, Jupiter, and Saturn, we see they have slower mean motions and longer periodic motions by comparison. We're going to need to measure three things from each of these curves to design a gear train that can reproduce them. The average slope, which represents the mean motion, the period of the periodic motion, and the amplitude of the periodic motion. There's one subtle alteration to make here, and that is to change from sidereal to synodic angle. This means that rather than measuring the angle relative to the stars, we measure it relative to the sun. We'll see why later on in the video. We can get the mean motion with the simple trend line, and once we subtract that out, we can measure the amplitude of the detrended data very easily. The period is a more interesting one. If we use the power of modern computing to do this with a Fourier transform, we can isolate the main signal that we're seeing. However, notice the secondary peaks that indicate additional signals. This is actually a clue that the solar system is heliocentric. It comes from resonance primarily from the eccentricity of Earth and the planet in question's orbit. Far too subtle to have been detected by manual observation, but a fun Easter egg in the data. We can repeat it for each planet, and then condense it down to this table of values. You can immediately tell that Mercury and Venus are not like the other three planets. They have no synodic rate at all. In other words, even though they are wandering back and forth a bit around the sun, all three move together as a sort of loose group through the sky. Both planets stay bounded within a certain angle from the sun, their periodic amplitude. Okay, now let's actually start building stuff, at least conceptually. For the movement of these interior planets, we can use a crank and slider mechanism like this one. It has the benefit of not only producing the needed oscillating motion, but it also moves asymmetrically in a way that oddly matches what we were just observing. More on that later. The length of the arm is determined to produce the right periodic amplitude, and the gear set powering it is chosen to produce the right period. All of the planets in my recreation of the mechanism, as well as the original to the best of our knowledge, are powered from the 1 year per rotation main drive gear. Here are the target gear ratios to translate from that 1 year rotation to the oscillation period of each planet, as well as the gears I ended up choosing. And here they are. This is part of the lower planetarium assembly. Mercury on the bottom has an 82 to 26 gear ratio to take that 1 year down to its 115-day period, and Venus, shown on the right, has a 62 to 99 gear ratio to go up to its 584-day period. I went ahead and added the colored pointers that will end up on the front dial for reference. When I manually rotate the input gears, you can see that asymmetric oscillation really come to life. In the full machine, these input gears are actually fixed and the drive gear is rotating. This is known as epicyclic gearing. I teased a little bit that there is a reason the motion is fairly accurate, and it has to do with a pattern seen in mechanical computers like this. It's not uncommon for the best way to generate an accurate output to be a scale model of the system that follows the same physical behavior. If I take this geometry, preserving everything at scale, and overlay it over a map of the solar system, we can see it's just a scale model of the orbits from the point of view of Earth. To finish the planetarium, we still have to handle our remaining 3 planets, Mars, Jupiter, and Saturn. Recall that these have a mean synodic rate, so they are constantly moving in a direction in addition to their back and forth movement. For these, we're going to use a very clever set of 4 gears to handle their motion. The purple gear is our 1 year per rotation input, and the yellow gear is our output that needs to be constantly rotating for our mean motion, but also lagging and surging with the periodic motion. The mean motion is pretty straightforward. We just need to choose gears that give us the correct speed at the yellow gear. This is a normal compound gear train where the output angle is linearly proportional to the input angle. Offsetting these gears produces a more interesting behavior, however. While the pin on the green gear is still moving at a constant speed relative to the green pivot, its speed is now variable relative to the orange gear, which produces that oscillating motion we're looking for. Tweaking the offset sets the right amplitude, and we'll need the output to be coaxial to the input, but that's everything to it. All 3 planets use this arrangement, with offsets and gear ratios selected to match their mean and periodic motion variables. If this seems a bit complex for such an ancient device, consider that we actually see this arrangement on the solar year to lunar month gear train discussed earlier. In the CT scan of fragment A, here's the pin and the slot of the stacked gears, and here's my reproduction of it. That's the offset pivot, and if I give it a manual spin, you can see the top gear speeding up and slowing down a bit. This one even has a variable phase shift for apsidal precession, but thankfully we don't need that in the planetarium. And here's the portion of the planetarium with the superior planets. The 3 input gears are fixed together at the top, each driving their respective pin gears. The pins extend down to the slot gears below, which then rotate the output gears in the center that transmit their motion up through coaxial tubes to the pointers. And that concludes the process for determining the planetarium geometry. So let's look at the next just for fun change, incorporating the equation of time into the assembly. The equation of time is related to a shape you may recognize, called an analemma. This is the shape that the sun traces in the sky if you record its position at the same time every day for the whole year. You can think of it as a 2-dimensional shape, with the vertical and horizontal components coming from different effects. The vertical portion is caused by Earth's axial tilt of about 23.5 degrees, and it's what gives us the seasons. The horizontal motion is in the direction that we saw the planets moving previously, and it takes the form of a more interesting dual sinusoid. This is the variation in the sun's motion, and since it is the direction that the sun moves throughout the day, it is also the variation in solar time. This curve is known as the equation of time. Equation in this sense meaning a correction that one would have to make from the sun's observed position to get the correct time. The Antikythera mechanism planetarium is thought to have had a primitive version of this, but going the other way, taking the time and determining the true sun position from it. The first known astronomer to identify this motion was Ptolemy, who wrote not only that there was such a variation, but also that it had 2 contributors and estimated each of their magnitudes fairly accurately. The red curve with a period of 1 year he called solar anomaly. That's known as the effect of eccentricity now that we understand it to be the result of Earth's elliptical orbit. The green curve with half the period was pretty much correct in cause, We call it the effect of obliquity, and it comes from Earth's axial tilt. Considering that Ptolemy's Almagest was published in the 2nd century, it doesn't feel too out of place to include it in our reconstruction. It's enough of an excuse to incorporate another really neat mechanical arrangement. The true sun indicator starts with the same 1-year drive gear as the planets, very convenient for our eccentricity component with a 1-year period, and 1 year to half a year is about the easiest gear ratio we've encountered so far, and that lets us get the obliquity rate as well. We need to take those 2 rotations, convert them to sine waves, and add them together in such a way that their different amplitudes are considered. How, you may ask? I present the Whipple tree, the most basic form of mechanical adder. Well, okay, this particular design has a few extra variables to play with. The objective is to move the purple arm, which will be attached to the true sun indicator, in a path that follows the equation of time. We've already looked at rigid body kinematics like this for the planetarium, but the equations of motion here are much more complex. If we use a small angle assumption to do it by hand, we get roughly the right curve, but it's not great. We again turn to modern computing in the form of an optimization algorithm to get a better match. All that's left is to build it. Once I had the rough pieces put together, I was curious how it ended up, so I did some primitive motion capture. Not as good as the perfect mathematical model, and there's probably some camera distortion in there, but good enough to illustrate the concept. Here's the final assembly running. The last just for fun change has to do with the use of crown gears, also called contrate gears, in the original Antikythera mechanism. Crown gears have their teeth cut in their face rather than their edge, and together with the normal spur gear allow for a 90-degree change in direction. However, they have a geometric problem where the teeth mesh. We can get one tooth to mesh easily enough, but as we go out from there, despite having the same tooth size, the radius of the crown gear causes the teeth to not line up. Functionally, this means these gears need a lot of slop in them to fit together, and are just meshing on the very tips of the teeth. Instead, bevel gears were used in these instances. They are significantly smoother, stronger, and I think they look a lot better on the machine. Bevel gears avoid the tooth meshing issue that crown gears have by sharing that 90-degree angle between the 2 gears, leaving both with the same curvature to the teeth and allowing them to mesh perfectly. Here are the 2 bevel gear sets that replace the crown gears from the original. On the left is the sun-moon differential that shows the moon phase, and on the right is the input gear on the crank. That's everything major that was changed, so let's lay it all out. Now there were just shy of 200 machine parts and another 100 or so fasteners to hold it together, so I used these layout sheets to keep everything organized by subassembly. Just like the original, everything is made as a matched assembly, so inadvertently switching 2 parts or installing a part backwards has potential to bind up or damage the whole thing. Making all these pieces was about a 10-month process and included making much of my own tooling. Specifically, a digital indexer is close to required to evenly space the gear teeth with the unusual tooth counts in the device. These can be purchased but are quite expensive, so I decided to make my own from a stepper motor, an Arduino, and an extra lathe headstock. I confess I didn't document the machining work very well, but I hope the number and complexity of some of the parts conveyed that it was quite extensive. My little lathe and mill were certainly pushed to their limits, and at some points I definitely felt the same. Many of the parts required fixtures to be made, and others had to be attempted several times before I got a viable part. About 90% of the build time was spent on these 2 machines alone. I did also make use of a water jet cutter for roughing out parts that needed to be made from plate stock, as well as cutting the metonic and serro spirals in the rear dial plate. Additionally, a laser cutter worked great for engraving the dials on the front and rear plates of the machine. For the largest gear wheels, my homemade digital indexer just wasn't rigid enough, so the laser cutter was also used for making custom indexing plates with 188 or 223 holes. To assemble it, we start at the back of the midplate, the structural backbone of the device. So far I've just added the 2 wooden feet to keep it upright. The first gear to be installed is called Q1, a 60-tooth gear. The naming convention was established by researchers of the device for all the gears in the original. Each arbor or axle gets a letter, and each gear on that arbor gets a number. To finish this cluster of gears, we add P, N, O, and M. M1 will be installed later since it's on the other side of the plate. These will eventually feed the Metonic, Calypic, and Games pointers. Next will be the Lunar Anomaly subassembly that we saw earlier, which requires a bit of construction itself. The large E3 and E4 gears create a sort of turntable, upon which the central and offset bushings are added. Gears E5, K1, K2, and E6 are then added to this side, and E1 and E2 on the other side. Let's add that onto our midplate and move on to the Ceros gears, that is arbors G, I, H, and F. These will eventually be connected to the Ceros and Exeligmos pointers. The last gear in this section is D2, which has to be inserted from the side somewhat awkwardly and is held in by D1 on the opposite side. We can now add the 8 support pillars around the perimeter and bolt the dial plate over top. Let's flip over to the front side of the midplate next. You can see D1 that was installed somewhat blindly before. Let's also add that M1 gear onto the M arbor. The C and L gears come next, leading the gear trains toward the center, where we'll add the support for the main drive gear and a thrust bearing. The main drive gear is another one that needs some pre-assembly. We'll connect the B2 and B1 gears together with a stainless bushing, as there's a lot of torque going through that connection. We'll also install some more support pillars while we have good access to the bolts underneath. Let's put that main drive gear on and move to the lower planetarium next. We've already seen how the True Sun gears work with their Whipple tree, as well as the Mercury and Venus gear sets, so let's throw those on and keep moving. The date plate is next to be installed and is held on by the next layer of support pillars, allowing us to continue to the upper planetarium. Each superior planet gets a slot gear and an output gear at this level. We've seen these before as well. You'll recall from our previous planetarium discussion that the superior planets also each get an input and pin gear. We'll do that on the side first. The 3 pin gears go onto this plate, generally called the superior planet plate. Then the 3 input gears are bolted together on a common collar before they join the pin gears. This top half of the upper planetarium then joins the lower half already on the machine. Before we put the front dial on, we'll add yet more support pillars, as well as this counterweight to keep the whole assembly balanced. With that done, the front dial goes on and is secured with 4 bolts. The front pointers are next. These are relatively straightforward, installed from bottom to top. We end on the moon indicator, whose central rod goes deep into the bowels of the machine to connect to our Lunar Anomaly train from earlier. The last things on the front are the input gears and their supports, and finally the hand crank. We'll finish up on the back dial, where the small pointers for the Calypic, Games, and Exeligmos dials are installed. Finally, the Metonic and Ceros spiral pointers from earlier are the last pieces to go on. With everything assembled, let's run through how it is used. The general principle is that the device has a single input and many outputs that all stay synchronized together, such that they can be compared. On the front dial, we have the day of the year, the moon phase, and the position of the sun, moon, and 5 planets along the zodiac. To make it more understandable, I've used modern months and included both the traditional zodiac dates as well as the true boundaries between the constellations. On the rear dial plate, we have the Metonic calendar spiral up top, which I've simply numbered with the 235 months and marked for each of the 19 years. On the original device, this was a more complex system that included intercalary years and hollow months, with the 5-turn spiral structure helping to lay out which days were skipped in which months. The smaller dial on the left indicates the Calypic cycle, a 1-day refinement across 4 Metonic cycles or 76 years. The dial on the right is called the Games dial. It shows a 4-year cycle of where the 2 Pan-Hellenic Games would have been held, between Olympia, Isthmia, Pythia, Nemea, Haleia, and Na. The bottom spiral dial is the Ceros cycle, used for eclipse prediction. I've used symbols to denote the anticipated eclipses between total, annular, and partial solar eclipses, and total or penumbral lunar eclipses. The small dial on the right is the exoligmos pointer, which is an 8-hour refinement across 3 Saros cycles. Because all of the dials stay synchronized, the device can be advanced or reversed until a certain input condition is met, and then the output of all the others can be read. For example, you could advance until Mercury goes retrograde and see what constellation that occurs in. Or see how long Venus will be visible at sunrise. Or what constellation the moon will be in at the next lunar eclipse. Or solar eclipse. All of these relations are why the Antikythera mechanism is often called an analog computer, and the sheer number of scenarios it can replicate because of its complexity is a primary reason that it remains one of the most fascinating objects of the ancient world. Certainly worth a few minutes to learn about, and if you're as captivated as I was, making your own. This was a rather challenging project to complete, and there were certainly numerous mistakes and lessons along the way. If you're interested in this type of mechanical astronomy, feel free to browse engineeringcommons.org, where I've written up guides on machining, astronomy, and horology topics. I do hope you've enjoyed this video, and that you've learned something new for the next time you look up at the night sky.